Investigate AR1 realizations. So we're going to really put together some of the things we've learned about AR1 models here. And really the best way to do it is just to play around with it. And that's what's so great about RStudio and TSWGE is we have a little laboratory here to just explore. So there's a function in TSWGE called gen.arma.wge. It allows us to generate realizations from AR models. So I'll say G1 equals gen.arma.wge, and I'll generate 100 observations from an AR1 real model. We'll say phi equals positive 0.9 here, and if we set a seed number, we'll all get the same realization. So if you type in this very code with SN equals 1, we should get the exact same realization, and it's about what we expect. I can tell you here that the mean is 0, mu is 0, and it wanders. It's got a certain starting point. It wanders up and down, but we know that it's a stationary process. It will always come back to the mean, as it does here. Great. So just to show the opposite side, let's say we did negative 0.9. Well, that'll have negative autocorrelation, and that will oscillate. And the closer, turns out, the closer we get to 1, the stronger that'll be. We'll talk more about that in the future, but certainly 0.9 is relatively close to 1. So if I went to, let's show how that works. Let's say I did now positive 0.99. So you kind of play around with that. So if I did positive 0.99, again, S equals 1, so we're all generating the same one, I might get something like that. And that is stronger positive autocorrelation. Each time point is more likely to be closer to itself. It's kind of where it's starting from. It's going to wander a lot more, and that's what this is doing. Some might even look at this and say that there's trend, but we know that there's not trend, right? We know that this is a stationary process. It will always come back to the overall mean. So let's explore that idea a little bit more. I'm going to let it go a little further, because right now it does look like it's just got this trend that we would call a random trend or a false trend, because we know how the data is generated. But let's just say I let it run a little bit longer. So if we stretch it out to 200, we'll still have the same 100. So let's go ahead and see that. So that's that same 100 we saw, and it keeps going. Even at 200, that's pretty extreme wandering, this 0.99, and we see that it's kind of flattened out a little bit, but it's still kind of up there. So let's give it a little bit more. Let's see what it does, right? Because we know it's got to come back to 0. So we let it go, and it's still going, right? So I might say, are you sure this is a stationary process? And this is just the first seed, right? See, SN equals 1. But it's still kind of climbing overall. But let's keep going, because we know it's stationary process. We know it has to turn back around, and it keeps going. It's unbelievable. But have faith, right? That's pretty, 0.99 is pretty strong behavior, strong wandering behavior. So at 500, it actually comes down a little bit. It's unbelievable, but it still goes up. So all right, well, why not? Let's just keep playing the game here, because we've got faith that that thing's going to turn around. And sure enough, it starts coming back down a little bit, but it's still well above the mean. It started down here. That was our first 100, and it has just overall climbed. But we know that it's going to come back down. And the more we play around with it, it's kind of stabilized a little bit there, because I generated the same amount. Don't you worry. There we go. You might still be a little suspicious, but let's go ahead and just kind of memorize that, right? That's the first about 900. We can remember that. Remember that big dip will be a good little landmark for us. Let's go out to like 3,000 observations here. Now that we've built all that up, boom, we do that. We see that we went up, 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 and then sure enough, we came down, and then we climbed back up, and then we came down. And if you wanted to look at the overall mean, you could do AB line of the, H equals, for a horizontal line, if you ever want to just get a reference point, mean of G1. And there it is. The mean of all of these points is about 0. We know that the mean starting off with 0, it'll wander back to the mean. Just to kind of really show that concept that's going to be important when we start forecasting with these models, let's take it out to 10,000 observations. take it up to 10,000, right? And there it was. That was our first initial climb, which looks pretty, right, pretty rare. That was a pretty extreme behavior there, but then it corrected itself. It came back around. At some point, it took a really kind of big dive consistently, but it came back up. It always will come back to the mean. Of course it is. It's a stationary process. Okay, so again, we're just playing around with it. I'll encourage you now to take the seed off and just see what else it could look like. So yours will be totally different than mine, but I get in there, and again, that's at 10,000. So let's look at, well, pretty clearly though, right? It's coming back to the mean every time. But if we want to see kind of what it looks like at 100, we'll get very different ones. That one's got that. We know it's a false trend, but it's kind of got the overall increasing. That one's kind of bouncing around. Wouldn't take us too long to randomly get one that had a pretty decreasing trend. There's another one that looks like it might have been increasing. That one might have been decreasing. That one might have been increased, but we know that they all come back to the mean. So again, if you pump that up to 3,000, you should see a pretty good example of it going up and coming down, going up and coming down, going up and coming down, and bouncing around. So let's explore a little bit more of the negative autocorrelation. So we'll come back over here, start back with 0.9 just to remember. Oop, negative now. We need negative 0.9. That's a good example of a non-stationary, right? That is more than 1 in absolute value. So TSWG is going to kick back. The AR part of our model is not stationary because we know in an AR1 it's very easy to see that phi1 has to be less than 1 in absolute value, which this is not, and thus its root is inside the unit circle, not on, but inside the unit circle. So if I corrected it to this one will be stationary, and that is the oscillating behavior. It's a little hard to pick out there because we've got 3,000 observations. We'll knock that back down to 100, and that's what oscillating behavior looks like. If you wanted it to oscillate stronger, then we'd have negative 0.99, right? That would be pretty strong oscillating behavior. It's up, down, up, down, up, down. If you want to see weaker, right, let's look at some weak oscillating behavior, right? That's still got some oscillating in it, but it skips a couple beats. If we want to see really weak, right, that's just kind of going around, but we can still see that oscillating behavior in it. And I hate to jump around too much here, but let's go back to positive. This will be weak wandering, right? That's kind of weak wandering, whereas that is stronger wandering. It's able to wander farther away from the mean. It's pretty easy for it to get all the way up to 10 when we know the mean is 0. But if we get back over here to 3, then it's really hard for it to wander that far away, right? Right off the bat, this one at 0.99 just wandered right up to 10. We knew it had to come back, but it's got kind of less gravity. It's able to wander a little bit farther away from the mean before it comes back. Whereas this one was 0.33, it's going to stay pretty much around the mean from the beginning. Awesome. So you might ask yourself, well, that's great. That's stationary. That's positive autocorrelation for an AR1 with positive phi, negative autocorrelation for negative phi1. When it's stationary there, we've got to have phi1 less than 1 in absolute value. But what happens if it is 1 or if it is greater than 1 in absolute value? So that's what this code will do here. I can set I'll have a variable called variance. I'll have my realization be 100. Phi here is 1.1. I'm going to knock that down to 1 right now. What happens when the root is on the unit circle? We know it's non-stationary, but what will it look like? This is P equals the length of the phi, which here is just 1. And we'll have to start with an initial value, right? The initial value here was about 0.5. So we have to start with a value. So I'll just pick a random uniform number between negative 10 and 10. And this is going to hold our realization. I'm going to generate this. We don't have a function for this because it's an academic exercise. But we do have, we can easily generate this. And it's good to see what's going on kind of relationship-wise behind the scenes. So this is xt. This is going to say from 1 to 1 in this case. It's going to grab that one initial value. It's going to put in the first slot there, random number between negative 10 and 10. And then for I in 2 to n plus p, which n is 100, so 101. So it's got the initial value, and then it's going to put the 100 extra values, the 100 generated values after that first one. So we'll have a array of 1 here. So that's xt1, the next observation or the next piece of the realization will go from I minus 1, so that will be 2, so that'll be again 1 to I minus p times phi plus r norm 1. So this is the random piece. This is multiplying. This is saying 0 mean, and it's saying the next observation is phi times the observation before it, plus some random noise that's normally distributed. We're grabbing one of those with mean 0 and variance 1 in this case. And then we'll end up plotting them after it does that. So here we go. At 1, it will wander, but wander quite a bit, right? We don't, we'll talk a lot more about non-stationary models and what that generates, but notice that it's just able to wander all the way from -5 to 10 pretty easily. And if I was to extend that out to 300 and run that, right, it can go down and then it can fly back up. That turns out to be relatively useful. We're going to talk a lot more about when roots are on the unit circle, because that turns out to be useful behavior that occurs often in the processes that we want to model. However, what happens when we just make this a little bit bigger than 1? When we make that root inside the unit circle, not on the unit circle or outside the unit circle, what happens then? So we'll show that. We'll do this. And explosive behavior happens relatively quickly, right? We can even knock this down to 100 observations, right? What happened? That's 1,000 observations, right? We can even see the dots here, but it stays relatively stable. But at 1.1, it's going to start explosive, and this explosive up, or it could explode down. It's just based on the random noise. If it happens to have a few more positive ones, it'll start exploding up after a while. If it happens to have a few more at random negative ones, it'll explode down for a while, or eventually it'll explode down. So if we run enough of these, we'll see it turn around. There it goes. So again, that's just based on the random noise. So that turns out not to be very useful because there's not a lot of processes where that will be where that model in nature that will be easily modelable with a phi1 equals 1.1. So we will restrict our use in the AR1 to phi1s that are less than 1 in absolute value, but noting that when we talk about non-stationarity, roots on the unit circle and thus phi1 equal 1 will be useful. So great job. Get out there. Please keep playing around with TSWGE and AR1s, and it's a great way to learn. Talk to you next time.